We've seen how SR and JK flip-flops give us complete control over logic states. But sometimes having two separate inputs to manage is overkill. If you just need to store a single bit of data or flip a state on and off like a light switch, dealing with two input lines adds unnecessary complexity. This diagram shows our solution, the single input flip-flop. We can streamline an SR flip-flop to create a D or data flip-flop, and we can simplify a JK flip-flop to create a T or toggle flip-flop. For both of these new components, the clock signal remains the heartbeat of the circuit. Nothing changes without an active clock edge. To track those changes, we use specific terms. We look at the present state, called Qn, and figure out what happens on the next clock pulse, which is the next state, or Qn+1. Stripping away that second input line makes calculating that next state incredibly straightforward. That predictability makes these streamlined components perfect building blocks for massive memory banks and complex counting circuits. Let's start with the SR flip-flop. Its biggest vulnerability is the forbidden state. If a circuit accidentally sends a high signal, a 1, to both the set and reset inputs at the exact same time, the outputs become unpredictable. This schematic shows how we fix that vulnerability. We tie S and R together into a single input called D, dropping an inverter right before R. Now, whatever enters S, the exact opposite arrives at R, completely eliminating the forbidden state. This truth table shows how clean the logic becomes. Whatever value is present at the D input simply becomes the next state on the active clock edge. If D is 0, Qn+1 is 0. If D is 1, Qn+1 is 1. You'll also hear this called a delay flip-flop. When we look at the waveforms, you can see why. The Q output exactly mimics the D input, but the physical output is shifted right by one clock cycle, creating a deliberate delay. By stripping out the forbidden state and predictably holding onto a value, the D flip-flop operates as a perfectly stable 1-bit memory cell. The JK flip-flop has a different strength. It's designed to toggle, flipping its state from 0 to 1 or 1 to 0 whenever both the J and K inputs receive a high signal. This diagram shows how we isolate that toggling behavior. We take the J and K input lines and merge them together into a single line, which we call T. With a single input, the rules condense down to two lines. If T is 0, the flip-flop holds its value. If T is 1, the flip-flop toggles, and the next state becomes the exact opposite of the present state. Here's a quick challenge. Look at this timeline. If we hold the T input at a constant 1 across 4 clock pulses, what will the Q output waveform look like? Pause the video and sketch it out. Because T is held high, the output is forced to toggle. At the first active clock edge, Q flips from 0 to 1. At the next edge, it flips from 1 to 0, continuing back and forth. Take a closer look at the result. The Q output waveform completes one full cycle in the exact time it takes the clock to complete 2 full cycles. The frequency of our output is exactly half the frequency of the original clock signal. That predictable frequency-having behavior is the precise mechanism that allows digital circuits to measure time and step through sequences. This schematic shows figure 10.35, where we chain multiple T flip-flops together. By taking the Q output of the first flip-flop and feeding it directly into the clock input of the next, we use that frequency-having trick repeatedly, creating a divide-by-2 counter. As the signal steps down through each stage, the frequency cuts in half again and again. Each successive flip-flop coggles at half the speed of the one before it, which perfectly mirrors how binary digits iterate through powers of 2. This cascading structure is how computers count. Let's lock in our two single-input devices with a quick cheat sheet. On the left, we have the D flip-flop. D stands for data or delay. It safely avoids the SR forbidden state and stores exactly what it receives. On the right, the T flip-flop. T stands for toggle. It isolates the best feature of the JK flip-flop, flipping its state on command to divide clock frequencies. By reducing their inputs, these components sacrifice flexibility for absolute predictability. Mastering them gives you the exact tools needed to construct the memory banks and processor clocks running inside every modern computer.